Hello everyone. Thank you very much for coming here. So the title of our paper is Cost-Sensitive Boosting Algorithms. Do we really need them? And what I hope is that by the end of my presentation, I will have sown some seed of doubt in your mind about that. So, at the center of my presentation, at the center of our work lies the well-known AdaBoost algorithm. So, AdaBoost is an algorithm that has been studied very widely, has a very rich theoretical depth, and at the core, it's an ensemble method. So it constructs a strong classifier by using multiple weaker ones. And the way it trains these weaker classifiers is sequential. So each subsequent classifier attached to the ensemble is trained in such a way that it focuses on the examples that have been misclassified by the previous classifiers. At the end, we combine the classifiers we train across the round of boosting through a weighted majority vote. So, let's see some of the inner workings of the algorithm. We start with defining a distribution over the training set, a distribution of over the examples of the training set. So effectively, initially, each example is given the same weight, the same importance. And what we do is that in each round of boosting, we train a classifier, we calculate a confidence score for that classifier based on the weighted error of this classifier according to the distribution. And we also update the weights that we are going to give to the new classifier in such a way that more emphasis is going to be given on the examples that the model trained around T has misclassified, and less emphasis is going to be given on the examples that were classified correctly. And as we said, at the end, we perform a weighted majority vote on a test example. So when we receive a test example X prime, each classifier is voting for either the positive or the negative class, so either 1 or -1, and each vote is weighted by the corresponding confidence of the model. So, the question now is, how should we adapt AdaBoost to a cost-sensitive setting? So when we have different costs for false positives and false negatives, how can we modify the algorithm in order to minimize the expected cost? How can we make AdaBoost cost-sensitive? We were not the first people to ask this question. So in the last 20 years, at least 15 variants of boosting have been proposed that claim to make the algorithm cost-sensitive. The thing is that many algorithms have been invented and reinvented multiple times under different names. Most of them have been proposed as heuristic modifications of one or more of the steps of the algorithm described earlier, of the original AdaBoost. And many even treat the costs, which should be known characteristics of the problem, as hyperparameters to be optimized. So our approach is to take a step back. In the beginning, I mentioned that AdaBoost has a rich theoretical depth. What I meant by that is that the steps of AdaBoost can be justified through many different theories. For example, functional gradient descent, decision theory, margin theory, probabilistic modeling, and even more, game theory, information theory, dynamical systems, linear programming. So the weight update rule, the update of the distribution over the weights, and the way we set the confidence for each model can actually be derived by these frameworks. So our strategy into seeing whether one of the existing variants that claims to perform cost-sensitive boosting is actually doing what we need, or if we need a new variant, is to check whether existing variants or any proposed variants are consistent with the axioms laid down by these 4 theories. So if you give me a new algorithm, and the steps, as we described them, are consistent with these theories, then we're happy, and this algorithm actually performs cost-sensitive boosting in the way we would like. So let's examine each of these 4 frameworks one by one. Functional gradient descent. So boosting can be viewed as a procedure to minimize a loss function, a loss of the model that we are training, by taking gradient steps in some functional space. The way we update the distribution over the examples, the distribution of weights over the examples, is given as a direction of movement in that function space. And the confidence score by which we weigh each vote in the final decision for each classifier can be given as the step size that minimizes the loss function, the same loss function. So for Adabus, for example, here we would just input the exponential loss, and we would get the steps of the algorithm. Now, many of the proposed cost-sensitive variants were modifying either this formula or this formula, but they weren't being consistent into them both following from the same loss function. So by examining cost-sensitive boosting variants from this framework, we can ask, are both of these formulas for a proposed cost-sensitive variant following from the same loss function? So are they consistent with each other? And in fact, in many cases, as we said, they are not. Next, we can check the way by which Adabus or the cost-sensitive boosting variants make decisions. So if we have a cost-sensitive problem, and our goal is to minimize the expected cost, the risk, and we have access to a probability estimate, then the solution is simple. We just shift the decision threshold to accommodate the costs, to make it easier to classify the important class. But in fact, many of the cost-sensitive boosting variants proposed do not actually implement this decision rule. And notice that now I'm not questioning whether the probability estimates are good. This is what I'm going to do in the fourth theoretical framework I'm going to be using. So, the next theoretical perspective by which we can examine cost-sensitive boosting variants is margin theory. On the x-axis of this graph, I have the quantity we call the margin. So what is the margin? The margin is a combined measure of correctness and confidence in our classification. A negative margin means that we classified an example, that we misclassified an example. A positive margin means that we classified an example correctly. Now, the dashed line here is the loss function of Adabus, the exponential loss. This step function here is just the 0-1 loss. So it's the loss we incur when mistakes of both types have the same cost. And what we see is that the exponential loss is smooth differentiable and it bounds the 0-1 loss. And that these are some of the reasons for why Adabus uses this function. Another reason is that as we minimize this function, we are maximizing the margin. So we're moving towards correct classifications with high confidence. And the margin theory of explaining Adabus has connected large margins, so increasing this value here, has connected this to good generalization behavior. So there exists some bounds on the generalization error in classification that if the margin is increased, the error is decreased. Basically, that's what they say. So in a cost-sensitive setting, we would expect to see an image like this. The blue examples have twice the value, let's say, of the green examples. And now we have two bounds. One bound on the green examples and one bound on the blue examples. And as the blue examples are more important than the green examples, we would expect this curve to lie above this curve for all values of the margin. And this is what we see here. So this is what we would expect to see, but actually some cost-sensitive boosting variants exhibit this behavior. So effectively, at some value of the margin, what happens is that the importance of the two classes is flipped. So from this framework, we can ask the question, does the loss function preserve the relative importance of each class under all margin values or not? And we can see that some do, some don't. So the final perspective is probabilistic modeling. So I mentioned at some point that I wasn't questioning yet the quality of the probability estimates. Now I am. Are the probability estimates generated by boosting good? And in fact, many people have noticed that they aren't, either in practice or in theory. And the reason is basically that this, by trying to maximize the margin to get good classification, we are leading the classifier to assign examples with high confidence to each class. So basically, the probability estimates get either go towards 0 or 1. So ideally, what we mean by good quality probability estimates, we would expect ideally a probability estimate to correspond to an observed probability, to an empirical probability. So we would expect these points to lie, if the classifier outputs a probability of an example 0.6 of being positive, we would expect 60% of the examples with that score, with that probability estimate to be positive. But this is not what we see in AdaBoost and in the other boosting algorithms. What we see is a picture more like this, a sigmoid distortion. So it either overestimates scores or underestimates scores. So the question we ask effectively is, are the probability estimates generated by AdaBoost and the other boosting variants calibrated? And as we see, the answer is no. If they were calibrated, they would lie here. So here are all the algorithms we included in the study. Here are the 4 properties we derived from each of the theoretical frameworks we described. And we see that, first of all, no algorithm produces calibrated estimates. So unless explicitly calibrated, they are distorted in the sigmoid way we described earlier. The other thing we notice is that these 3 algorithms here at the end satisfy every other property. So what if we were to calibrate these? And that's what we did in our experiments. And in our experiments, we used plus scaling, so effectively we mapped the sigmoid to correct for that distortion. We performed lots of experiments. I don't think I have time to go through them now, but feel free to approach me at the poster session or at any point afterwards. What we can remember from our basic findings basically is that the calibrated versions of these 3 methods that I said outperform their uncalibrated counterparts. These in turn outperform every other method because they satisfy the theoretical justification is because they satisfy every other property, and these fail to justify some of these 3. So one of these 3 methods that outperforms the rest is something we call calibrated Edakunni. So let's see what this is. This is just the original AdaBoost algorithm. And all we did was reserve part of the training set in order to calibrate it using flat scaling. And then during the deployment phase, we just shifted the decision threshold. So basically, by not changing at all the training phase, just by adding this calibration step and by modifying the decision threshold, we get a cost-sensitive boosting variant that satisfies all the properties we described, and that is versatile and performing top or jointly tied for best, let's say. So the take-home conclusion is that we analyzed the cost-sensitive boosting literature. This is more than 15 variants over 20 years from 40 different theoretical perspectives. And our main result, our main finding is that, in fact, cost-sensitive modifications to AdaBoost itself, to the training phase of AdaBoost, are not needed. All we need is to properly calibrate the scores, and when making predictions, just shift the decision rule, the decision threshold. So, thank you very much. Mille grazie. And please, if you have any questions, feel free to ask.
Thank you very much. That was perfect timing to start with, and a very interesting talk, a very in-depth evaluation. We have plenty of time for questions. It's a question right at the front here.
I have a microphone with this one.
Hello. May I? I'll just stand up. So, I'd like to ask you if any of these conclusions change if you use isotonic regression instead of flat scaling. Not sure if you're familiar with it.
Yeah.
It's a method that does not assume that there is a sigmoid shape in that plot that you showed.
Very good question. So we tried only one way of calibrating the probability estimates. And on top of that, we didn't even try to optimize. For example, we just split the training data in half and gave half of it to the training method and half of it to the calibration method. As you said, there are other calibration methods. We picked flat scaling first because in previous studies it has been found in the case of boosting to perform better. Because in the case of boosting, we know that we have this sigmoid distortion. It would be interesting if somebody tried the same thing with isotonic regression or with some other way to calibrate. So I don't know the answer, but you're welcome to try.
So thank you also for a very nice talk. My question is whether if you perform similar experiments with logic boost, in which you minimize logistic loss, and the question is whether in that case you need also calibration or logic boost is calibrated better or something like that?
Again, I believe in that previous study they also tried logic boost. So they examined logic boost, isotonic regression, and the flat scaling of the scores that the way we calculate them in the paper, and they found that in the case of boosting, the latter performs the best with limited data. So again, so our point was basically trying to say that, you know, these algorithms, if we calibrate them, we correct for the tendency of other boosts to not produce good probability estimates, and then we can just apply decision theory. But again, I would like to see people try other loss functions or other variants of boosting. It's in the same vein, basically.
Question in the back.
Do you think your general conclusion is more general than for boosting, in the sense of, like, seems like what you've shown is that to do cost-sensitive learning, what you need is a machine that produces calibrated probabilities followed by a decision theoretic boundary that's based on the costs, rather than muddling up your learning algorithm with some cost-sensitive tweak. Would you go so far as saying that's probably true for all other learning methods?
Yeah, that's a very good question again. I wouldn't go so far as to claiming this, but I would go so far as to having it as one of the next things I would like to explore. And also one more thing, even if it's not always better, it's still more versatile, so you don't need to retrain. So it does still have some benefits.
Actually, you observed, yes.
Yes.
You observed that all the methods you tested do not generate calibrated probabilities. But isn't this inherent in any cost-sensitive method? Because my intuition is that generating calibrated probabilities means generating probabilities that have good probability theoretic properties, while cost-sensitive methods generate probabilities that have good decision theoretic properties. So isn't this inherent in any cost-sensitive method?
It is, but you can correct for it, in a sense that you can take this cost sensitivity away by reweighting the estimates in some sense. But the reason why boosting estimates are not calibrated is basically this margin maximization property. So they are trying to be as confident as, even the unweighted data boost is trying to make predictions that are either predict 1 or 0 as a probability estimate. And this is the case with all other boosting variants as well. And it's inherent in the fact that they are an additive model that has an exponential function with the confidence weights being something which has a logarithm, and then this effectively becomes a product of experts. So in the paper we also give We also phrase the probability estimates of ADA boost, and we can do the same with all other boosting algorithms as products of experts. And effectively, it's because of this product of experts form that you will have this distortion, even if you try to account for the costs, for the cost sensitivity to take it out.
Yeah.
Question in the back.
Are you familiar with any publicly available cost-sensitive datasets?
We use the
Or are
UCI.
your data sets available?
Yes, our datasets are the UCI datasets, basically. So we just said that false positives, for example, are 2 times or 5 times more expensive than false negatives.
That's what everyone is doing, but I wonder if there are any real datasets that have known costs.
Well, I'm not sure. I just use the UCI datasets, to be honest. So,
Thank you.
I'm not seeing any questions right now, so I can add in one of my own. Following up on the question we heard earlier, would it be fair to say that actually your experiments show that calibration is the thing, and the things that you argued for, the 3 important properties, are maybe not so important? So in other words, did you actually calibrate all of them when comparing them, or did you calibrate only the ones you liked because they met all the other properties?
it's mostly like the second. But if you examine the other properties, one of them is really important. One of them is, suppose I have probability estimates. Am I building a Bayes optimal classifier? So this is pretty important. The first property I described, I simplified a bit in this presentation, but it also has the aspect of, is this a loss function of the model I'm building? And it turns out that some algorithms, for some algorithms, it is not. So they are making predictions using one model, but they are deriving the updates, let's say, using some other model, which is weird. So I haven't tried to calibrate everything. I did exactly what you said and what I described here.
Okay. Well, thank you very much.
Thank you.